So I believe this will be our last video on the characteristic equation, which is section 5.2. So we were looking at some theoretical results that we were able to derive from using the characteristic equation. Here's another really big one about eigenvalues. This one is a really big result, theorem. Let's say you have an n by n matrix. If A is an n by n matrix with n distinct eigenvalues. So the maximum number of eigenvalues you can have is n. Let's say we have exactly n distinct eigenvalues. So no repeated eigenvalues of like multiplicity 2 or multiplicity 3, but they all have multiplicity 1. So A is an n by n matrix with n different eigenvalues. Lambda 1 will be the first one. Lambda 2, we'll call the second one, and so on and so forth. Through lambda n, that'll be the nth one. So lambda equals lambda 1, lambda equals lambda 2, through lambda equals lambda n. Those are your distinct eigenvalues. If this is the case, if you have n distinct eigenvalues, then the determinant of just the matrix A, we're not talking about A minus lambda I, the determinant of just the matrix itself is the product of the eigenvalues. It's going to be lambda 1 times lambda 2, so on and so forth, times lambda n. So that's a big deal. If you have n distinct eigenvalues for an n by n matrix, the determinant of that matrix will just be the product of the eigenvalues. Let's prove this. This is a pretty neat thing, I think. So let's suppose A is an n by n matrix with n distinct eigenvalues lambda 1, lambda 2, and so on, lambda n. All right, and what does that mean exactly? Let's focus on our characteristic polynomial. Our characteristic polynomial. So our characteristic polynomial we call what? Determinant of A minus lambda I, or lambda in. Now remember that this is going to be an nth degree polynomial, right? When you have an n by n matrix, you're going to have an nth degree polynomial. And because we have n distinct roots, we're going to have n distinct factors, right? Our first factor is going to be lambda 1 minus lambda. That's our first factor. So we're getting that basically, if you look here, at our first root, lambda equals lambda 1, basically just subtract lambda from both sides and you get 0 equals lambda 1 minus lambda. And so on and so forth. So then our second factor would be lambda 2 minus lambda, and so on and so forth. And our last factor would be lambda n minus lambda. So that is how our characteristic polynomial is going to factor. It's guaranteed to factor in that way because we have those n distinct roots, right? Lambda is lambda 1, lambda is lambda 2, lambda is lambda n. Now, let's think about this carefully. I'm going to set lambda equal to 0 right now. So lambda is functioning like a variable here, right? It's functioning like a variable. It's kind of like replacing the x. So we're going to set lambda equal to 0 and see what happens. What happens when I set lambda equal to 0? I'm just going to end up with what? Determinant of A, right? Because when I set lambda equal to 0, I'm going to have 0 times the identity, which is going to be the 0 matrix, and A minus the 0 matrix is going to give me A. So I'm just going to have determinant of A equals, we're going to have what? Lambda 1, lambda 2, dot, 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 and so on and so forth, lambda n, right? When we plugged in 0, 0 for the lambdas, those things just zeroed out. So we can just lambda 1, lambda 2, lambda n. So what is that? That's precisely what we wanted, right? We wanted the determinant of A was the product of the eigenvalues. That's what we have. That's the proof. Really pretty proof. So thus, the determinant of A is the product of those eigenvalues, lambda 1 through lambda n. Pretty impressive. All right, so we want to do one more thing that is going to be useful for probably our later section, section 3. We want to introduce a new concept called similarity of matrices. We've actually seen this a little bit in some problems in the past and some homework, but we never officially defined it. So let's go ahead and officially define what it means for two matrices to be similar. We say two square matrices, n by n matrices, A and B, are similar. That's what we're defining. Two matrices are similar, provided the following happens. There is an n by n invertible matrix P such that the following happens. A equals P, B, P inverse. So you want to remember that equation. A is similar to B if and only if A equals P, B, P inverse. And this is for some invertible matrix P. Some invertible matrix P. Okay. So, really big result. This is going to feature later down the road. If A and B are similar matrices, then they have the same eigenvalues. Then they have the same eigenvalues. This is going to be really useful in our next section, dealing with similar matrices. Proof. Okay, we want to prove an if-then statement. So here we're going to assume A and B are similar matrices. So let's suppose A and B are similar. That's strange. Let me get that extra bit up there. What does that mean? That means then A equals P, B, P inverse for some invertible matrix P, for some invertible matrix P. All right. So now we want to focus on the eigenvalues of A and then try to figure out how they compare to the eigenvalues of B. Now I'm going to start with the eigenvalues. Let's start with the eigenvalues of B first. Eigenvalues of B. So note lambda is an eigenvalue. Of B, if and only if what? If and only if what? Determinant of, let me get rid of this. Okay, there we go. Determinant of B minus lambda I equals 0. Except this time I'm not going to put the 0 on the right, I'm going to put the 0 on the left. You saw me do this just a moment ago in the other video. Right? Lambda is an eigenvalue of B if and only if the determinant of B minus lambda I is the identity. Now I'm going to do a trick here. I'm going to multiply this by a form of 1. determinant of the identity. Remember the identity matrix has a determinant of 1, right? You think about the identity matrix, it just has 1s down the main diagonal and 0s everywhere else. So when you take the determinant of the identity, it's just the product of the main diagonals, which is just a bunch of 1s. The determinant of the identity is just 1. So that red right there, determinant of the identity is just 1. So I'm just multiplying my blue matrix, determinant of b minus lambda in. I'm multiplying that blue determinant by a form of 1. And now I'm going to do a little trick. We know that the determinant of the identity, well, another name for the identity is what? P times P inverse, right? P is an invertible matrix, so P times P inverse is precisely the identity matrix, right? So I'm just splitting up the identity into P times P inverse. And then we got this blue determinant of B minus lambda in. Now we have a property of determinants that says we can separate determinants. Determinants are multiplicative functions with regard to matrix multiplication, so we can break this into the determinant of P times the determinant of P inverse, like so. And then we got on the end this blue determinant of B minus lambda in. Now these determinants, these are not matrices, right? They're just numbers. So you can change the order of determinant multiplication. You can't change the order of matrix multiplication because matrix multiplication is not commutative. But determinants are just numbers, so numbers commute with respect to multiplication. So I'm going to change the order. I'm going to do determinant of P first. Then I'm going to do the blue determinant second, determinant of B minus lambda I second, and then I'm going to put the determinant of P inverse in the end. That goes in the end. And now we're going to reuse the multiplicative property to combine these three determinants into one. So we're going to put these determinants into one big determinant. It's going to be determinant of, so we're combining these together. We're going to have P on the left multiplied by B minus lambda I in the center. And then we're going to have a P inverse on the right, right? We just combine those into a single determinant. That's called using the multiplicative property in reverse order. Rather than breaking these up, we put things back together. All right, now let's distribute the P here. Distribute the P here on the left side. So when I distribute the P here on the left side, I'm going to have what? PB, and then we're going to have minus lambda PIN. And then on the right, we're still going to have that little P inverse there. We haven't distributed that through. So I multiplied the red P through here. And I have PB minus lambda PIN. Now let's clean that up. All right, this is determinant of, let's see, PB minus lambda P. All right, lambda P, because when you multiply here, P times the identity, you get P. Okay, and then we don't want to forget on the right here, we have what? P inverse, right? P inverse. Now, so I've distributed the P through on the left. Now I'm going to distribute the P inverse through on the right side. See if we can do that. So the P inverse is going to get distributed through on the right. So we're going to have PB, P inverse, minus lambda P, and then P inverse. That's distributing the P inverse through, coming from the right side. And here we go. Determinant of, does anyone remember what PB P inverse was? If we go back and check, remember A and B were similar. And we had right here that A was equal to PB P inverse because A and B were similar. So we're going to replace PB P inverse right here in purple with an A. And then we're going to have a minus lambda. Here's another question. What's another name for P inverse? P inverse is what? The identity. So what we have is that the determinant of A minus lambda I is equal to, if you follow it all the way back, if you follow this all the way back, see the string of equalities? It's equal to this guy right here, right? It's equal to 0. If you just follow that string of equalities, we have crap. Let me erase that little green mark on the side. You follow it back, we have 0 is equal to the determinant of A minus lambda in. So this is equivalent to saying, well, please write, thank you. Equivalent to saying that A minus lambda, I'm sorry, lambda, where's lambda? Is an eigenvalue. Lambda, this guy, is an eigenvalue of A, and that's because the determinant of A minus lambda I is equal to 0. That's the end of the proof, right? What did we start with? We started with A and B are similar, and we showed that lambda is an eigenvalue of B if and only if, follow the arrows, lambda is an eigenvalue of A. So A and B will have the exact same eigenvalues when they are similar matrices. Yeah, so that's exactly what I wanted to prove. They have the same eigenvalues. Pretty neat, pretty neat. So, yeah, I guess next we'll move into 5.3, which is about diagonalizing certain types of matrices.